Good afternoon. Welcome to the course Thermodynamics of Materials. Today we are into lectures 161 and 162. We are discussing the Gibbs phase rule. Last day we actually found this expression A is C prime minus P plus 2, where C prime is the number of species and P is the number of phases and A is the degrees of freedom. So this actually we actually reached up to this point. So today, before we start, for the sake of continuity, let us first write down the last few lines of the last class. So the total number of variables. Actually, another thing is this is already written at the beginning. The purpose of the study of Gibbs phase rule, the purpose is to determine the number of independent variables called the degrees of freedom which are required to define the state of a system at chemical equilibrium. This is actually we actually what we mean by the degrees of freedom and what is the purpose, the derivation. The purpose is to find an expression for the degrees of freedom. So that is actually we actually got this expression, but this will be further modified into the final form, where C prime will be replaced by C, the number of components. So this part will be taken up today. So this is actually initial statement that we have I written here, and this is a kind of actually diagram that shows actually this number of phases alpha, beta, gamma, delta, they call epsilon, and each phase contains this species I, J, K, numbering C prime, and alpha, beta, gamma, delta, epsilon. These are the number of phases, P phases. So this is written here, P phases and C prime species. So this was all discussed last day, but just for continuity. And so start. So let us first write down the last few lines of the last class. The total number of variables required to define the state of the system containing C prime species distributed over P phases in terms of temperature, pressure and composition. Composition is given by mole fraction of the species. Mole fraction of the species yes, temperature, pressure and compositions defined in terms of temperature, pressure and composition, mole fraction of the species. You can add here in terms of temperature, pressure and composition is pieces in each phase is maybe right. I may write here. Hmm. Uh, I can add here species in each phase. In each each phase composition in terms of mole fraction of the species I, J, K in each phase, that is Xi, Xj, Xk, etc. Each phase. So is how many? This was shown to be total is how many? Was actually this was C minus 1, C prime minus 1 plus 2 into P times C prime plus 1. That's it. P times C prime. So let us repeat quickly. For the break, the total number of variables required to define the state of the system containing C prime species distributed distribution in P phases in terms of temperature, pressure, and composition. Composition is expressed in terms of mole fraction of the species in each phase. Is how many? This total number of variables is P times C prime plus 1. Of this, of this total, the number of restrictions upon the independent choice of temperature, pressure, and composition is independent choice. There is some restriction. Okay, so this number we found the number of restriction upon the independent choice of temperature, pressure, and composition at equilibrium, because equilibrium gives rise to certain constraint, some restrictions, relationship. So independence, actually there is some dependence uh, among the variables. So if we consider this part, so number of independent choice will be how many? I'm sorry. Of this, the number of restrictions upon the independent choice of temperature, pressure, and composition at equilibrium, which is also the number of dependent variable. This is P minus 1 times C prime plus 2. These both we actually showed last day. Actually, we went up to this point. So, hence, the degree of freedom, what is that? The number of independent variables. See here, number of independent variables called the degrees of freedom. So, the number of independent variables. So, we have to, that is called F. F is obtained as F is, this total is what? P times C prime plus 1 minus this number. These are the dependent ones, mutually dependent. So, if we eliminate this from this total, then we will get the real independent variables, which will be able to describe the system at equilibrium. And this number is called the degrees of freedom. So, this total minus these restrictions. Okay, this comes from the criterion of equilibrium. From the criteria of equilibrium in terms of temperature equalization, pressure equalization, and chemical potential equalization. So these are the restrictions imposed. So that means all of them are not independent. So all of this cannot be independent. How many? You have to subtract these numbers, which are actually the dependent variables or restrictions or equalities or equations, whatever you call. The number of us you may call these restrictions or dependent variables or equalities. How many equalities? Okay. So pressure alpha is pressure beta is pressure gamma, equalities or equations, whatever you call these dependent number variables or dependent. Okay, what is this called? Restriction, number of restrictions or number of dependent variables, which is number of dependent variables is this. So subtract this one, this dependent variables or restriction, number of restrictions from this total, and if you do this, you have this, and then it is actually coming as C prime minus P plus 2. So this much is okay. So today's class begins from here. So because we went up to this, today we have to, I give you the answer. It will be C minus P plus. I give you the answer. We are currently at C prime is the number of species. We will reach up to C minus P plus 2, where C is the number of components. So this one is still pending, this job. It is not yet completed. So we will continue from this point. Okay. So let us move on with this. Let us consider under what happens. Actually, now move on. Now, if it is considered that one thing I tell you, what I am going to consider now, the factor that we have not so far considered. Remember, I wrote at some places, we have seen actually there that we consider only phase equilibrium, and I said chemical equilibrium entails phase equilibrium as well as reaction equilibrium. Reaction equilibrium will, we said that reaction equilibrium would be considered subsequently later. Now is the time to consider reaction equilibrium also. That means species undergo chemical reactions which we didn't take into account previously, and we reached up to this point. So if you consider this, that now the species may undergo chemical reactions among themselves. Okay, so this will consider the number of chemical reactions, independent chemical reactions. This will count actually how many. So if it is considered that the species enter into the species enter into R number of enter into R R number of R number of independent independent chemical reactions independent chemical reactions like like just some examples: I plus 2J the species, 3K I, still another is I plus J is L, IJKL, these are the two L rather. Okay, it can be anything. Okay, L it can be also. So etc. etc. So how many total is R? One thing you note here that note these are independent chemical reactions. So if you can construct another reaction, other reactions from this, how construct by addition, subtraction, etc. So I am suppose adding these first two. Note 2I plus 2I plus 3J goes to 3K plus 2L obtained by adding these two, obtained by adding the first two cannot be treated as a can be treated as an independent chemical reaction. chemical reaction. Don't you cannot consider this. Okay, so the these are just so p number of r number of independent chemical reactions are there. So you should careful. Another example is this. A very good example. Another example. Another example. Another example. This is very useful. Suppose carbon and oxygen. So C plus half O2 is CO and C plus O2 is CO2. These two are independent, mutually independent. So, okay, so they may constitute this R number of independent chemical reactions. But this is okay. These two are okay. But don't okay. These two are okay means these are okay. These are okay. But okay. But CO plus half O2 is CO2. This is not independent anymore. These two are independent. Yes, Gibbs say independent, but this is not independent. This is obtained how? By elimination of carbon from these two. Addition subtraction. So this is not. Similarly, another one CO2 plus carbon is 2CO is again not. Is obtained from here by eliminating oxygen. So this is so out of four only two independent. Be careful about this point. Okay. So independent number of independent chemical reactions. Independent. You underline if you are interested. Independent. But another thing, remember, must these be independent or must these be independent? These two? No. Two independent. The number matters most. Number is most important rather than who they are. Two independent. CO system, two independent. So it is possible these two are independent, these two are dependent. Thanks. Two, in any case. It is also possible this is independent, this is independent. In that case, this is dependent. I think you have understood this. So be careful about this part. Okay. So never write. We can write so many things. You cannot. This is actually very easy. The example is what I have shown here. This cannot be treated as an independent chemical reaction. So good. So this is okay. This gives so etc. So I am removing this. This side is I am removing. This is not needed. I think you have understood. Then, like if it is considered that the number of compositional, now use the property of chemical reaction equilibrium. Additional equality is coming. Equations coming means restrictions coming. Additional. So see, the number of compositional restriction compositional restrictions further increases. Further increases by R. Restriction increases means dependent variables increasing. Okay. So by R, following means you are subtracting this, you have subtracted this, but still another R coming here, and that will be subtracted from the total. So this will be taken care of soon by R following the condition following the condition of reaction equilibrium which is for the above reactions which is reactions which is for the above reactions. What are the delta G is 0 again, phase equilibrium or reaction equilibrium, both are chemical equilibrium. Delta G is 0. This is what is this? So if I apply this, what you write? Product reactant partial molar phenyl G is 3 bar, 3 bar, and here in the second one Gi bar plus Gj bar is 2Gl bar is okay. So this etc. So P number of restrictions coming, Gi bars coming means it will lead to actually Gi bar is RTL and activity. Activity means composition. So compositional restriction finally it can be shown. Okay. So like phase equilibrium here also these are the among the reaction among the species. Okay. So this is P number. Sorry, R number. R number increases by R. So these are valid for all P phases. All P phases. So given this, next we will I am actually removing this. This is already okay. Let us write. Let's give a star here. Star here. What is this? Thus, including R, R reaction equilibria well, R reaction equilibria including R reaction equilibria, the degrees of freedom can finally be written as, write this, F is what? This already there, C prime minus P plus 2, it should be even less, further less by R. R restrictions are there. Here restrictions, these were the restrictions P minus 1 C prime plus 2. So there is additional another one. So minus R. So minus R means this is minus R. This is the answer. Then what you will do? write this C prime minus R together minus P plus 2. I call this C prime minus R is call this C minus P plus 2, the famous phase rule. What is C? C is the number of components. So this is actually where C is where C is the number of components of the system, and thus can be defined as what? Defined as C is what? C prime minus R. C prime minus R, that is C prime is number of species that is the C prime minus number of independent reaction equilibrium. Independent reaction equilibrium. This is your C. Definition: when R is 0, so when R is 0, number of components, R is 0 means number of independent reaction equilibrium, no chemical reaction occurs between the species. Okay, only phase equilibrium exists. Okay, so number of components is in that case is number of species. This is also we have followed this when R is 0. The formal definition, even so there is a formal definition for the another definition of the formal definition of component. You box this also. F is C minus P plus. This is called the phase rule. This is the phase rule. Okay, so write somewhere. Okay, this okay. This is the phase rule. Shall I write somewhere? Okay. It's okay. I will write this. This is the phase rule, the Gibbs phase rule. Okay. So the formula of component, definition of components C. What is this? The number of components. You may call it alternative definition, but this may be considered formal definition of component. The number of conceptual definition. This is actually kind of mathematical definition. Very easy also. Number of species and number of reactions. You get number of components. Number of component is actually maybe confusing. So you should be careful. You should follow both definitions and we will use both of them. Given equation, this is equation number 1 and this call this equation 1. This will be important. Equation. The number of, so here the formal definition number of component of a system is the minimum number of elements. This is the minimum number of elements. Is okay there? You can see this. This last. I can. It's okay. Minimum is the minimum. It's okay. Is the minimum number of elements. So underline elements. Okay. That is the what is the minimum number of elements is that is the number of elements whose moles are not stoichiometrically bound. So minimum number of elements that can describe the composition of each phase of the system at equilibrium. At equilibrium. At equilibrium. Thus, C is number of elements minus number of stoichiometric restriction on composition of each phase. on composition of each phase. So this is also box this. This is another definition in terms of number of elements. So call this equation 2. This is equation 1. This is C, this is C. We will consider both of them and we'll see they will coincide or they will be in agreement and they will give the same result. Then we will be very satisfied that the evaluation of C is correct. So we shall so here just another thing. So when this is very important. So when the number of stoichiometric relation restrictions is zero, number of components is number of elements. This is a corollary. If this is zero, these two are same. Here also, if this is zero, R is zero, then these two are the same. So number of components is number of species. Here number of components is number of elements. So this will occur often. Stoichiometric restriction will not come across often. So you rarely come across. Okay. More often than not is what that there is no stoichiometric restriction means it is zero. More often than not, this will be zero. So often you will see number of components turns out to be number of elements. Very easy. And here also number of species very easy to count minus number of independent reaction equilibrium, which is equally easy to find out. So you will get C here. And then you cross check these two values, and if they are same, then you are very satisfied. So that you are sure about the evaluation of the number of components. Okay, this is your okay. Now there is further clarification. Elements, why this? What are these things? Okay, how do you express the composition of each phase with minimum number of elements? What is this? Okay, when there what under what condition you have stoichiometric restriction? Let us take some examples, and then you will understand this formal definition of componency. Okay, in terms of number of elements. So remember, this is in terms of element. This definition of component is in terms of number of elements. Elements like say iron, carbon, oxygen. Element that periodic table elements. Okay, the number of elements that you have 103 or 110. So these number of elements like say okay, hydrogen, carbon, oxygen, nitrogen, sulfur, phosphorus, etc. So iron, manganese, all these elements, and this is species. This is in terms of number of species. Okay, very good. So let us move on. We shall try both definitions of C, both definitions of C, 1 and 2, 1 and 2 in case it is necessary to cross check, in case it is necessary to cross check the value of C or to avoid any confusion, or to avoid any confusion. This, but yes, we will take up some confusion. Okay, examples. This will help you. These examples. Okay, first is easiest, simplest one. M solid plus oxygen gas MO2 solid. Try to find the value of C for this system, a reaction system, or the system. Okay, value of C using either definition, 1 or 2. So let us see. First of all, first is what? C is what? Number of species minus number of independent reaction equilibrium. So write that number of species short, number of species minus number of independent reaction equilibrium or equilibrium. Okay, how many it is? How many species? 1, 2, 3. 3 species. 3 minus independent reaction, only one reaction we see, the reaction that is written. 3 minus 1. So is 2. Species are what? Yes, species how many? That's number of species is what? Species how many, or who is M O2, M solid you may write, M solid, O2 gas, and MO2 solid. How many? These are 3. Total 3. So 3 I have written here. Number of species. Minus 1 is the number of independent reactions. The reaction it is shown. So 2 we get using this definition. Equation 1. In terms of species. Let us see in terms of elements. See alternative definition. Formal definition or alternative definition. Alternative definition in terms of elements. So what is how many elements are there? We will write straight away. 2. What are there? Is right here number of elements is number of elements. Number of stoichiometric restriction, no, you will see. There is no restriction. I will give you example where there is restriction, you will very easily understand. But there is no restriction. Elements M and O2 are not bound here. Okay, see, it is not all phases. Here maybe, but it is free, oxygen free. Here M is free of oxygen. Here oxygen is free of M. No more. And MO2. Okay, so there it is bound, but not in all phases. Okay, so all phases not. So number of elements only. So no restrictions. No stoichiometric restrictions. No. Stoichiometric restriction is not there. So number of elements. What are these? We see clearly 2. Who are there? As I have said, like periodic table elements. Periodic elements. What are these? M. So M can be actually say Ti, titanium dioxide. Ti M, and another is elements you write in terms of elements, maybe O2 you can write, but MO, good, very good, elements, 2 elements, 2. So C is 2, C is 2. They are reconciled. They are in full agreement, fullest agreement, no clash. In fact, both concepts are very useful. Try to use both of them to have complete satisfaction, complete confidence over number of components. This will be used. Okay. So this is okay. The example 1 is very easy. Second example, I take this side. Second example is what? Is what I shall write. Calcium carbonate solid goes to calcium oxide solid plus carbon dioxide gas. We are not finding the degrees of freedom now. This task is here about number of components only, confined to finding number of components. The degrees of freedom will be taken up in the next section. We will use many examples where we will find degrees of freedom. That is later on, coming, soon coming. But here complete, clarify the concept of the number of components. And again we have considered another system, reaction system, okay, which is under equilibrium. So these are considered, okay. Like again find C. What is the number of species? Minus number of, I am not writing the independent reaction equilibrium, short. Number of reaction equilibrium, or number of independent reaction equilibrium, okay. Okay, number of reactions I may write also. So number of reactions, number of species, how many? Species how many? 1, 2, 3. 3 minus how many reactions? 1 is 2. Again write, species are what? What are the species? Species are what? Calcium carbonate solid, calcium oxide solid, carbon dioxide gas. Total 3. Okay, 3. Okay, how many? 3. 3. Okay, these are the 3 and minus 1, no, 1 reaction only. So 2. From this definition, we get C is 2. Let us see what we get from the definition of elements. Right. Again, C is alternative definition of this definition is what? Number of elements from element wise. Number of elements. If you consider only number of elements, how many elements are here? How many elements here? Calcium, carbon, sorry. Elements, calcium, carbon, oxygen. Elements, periodic table elements. Okay, periodic table elements. Okay, or say just elements. Calcium, carbon, oxygen. 3. So 3, it is 2 in class. C is 3. If now see here, actually, here these number of restrictions, stoichiometric restrictions apply. It is non-zero. It is not. It is non-zero. It is not zero. It is what it is. Okay. Minus. So you include this. This time you have to include number of stoichiometric restrictions. Stoichio restrictions. I am writing in short. How many? You know, number of elements is what? How many? These are 3 elements. Apparently 3. So 3 minus restriction is 1. What is that restriction? If it is included, restriction it is 2, and again these 2 and these 2, they are in perfect agreement. Okay. These are actually these okay. then they are actually reporting the same result. But one is what? What is the stoichiometric restriction? Note here. Note. Interesting observation. See, the observation is what I am writing. See, have you seen this? Here everything is bound. This compound, nothing is free. Here air is free, oxygen is free, but it is all bound. In this case, you will suspect that there is some stoichiometric restriction. What is I am writing for you is what? NO is NCA plus 2N carbon C. This holds good for each phase. This. This phase, this solid, this is solid. Solids are pure, so not in solution. This phase, calcium carbonate phase, calcium oxide phase, and carbon dioxide gas phase. This holds good, applies. I'll show you number of moles of. So if anything else is to write, I will let me check actually if you want to write. Okay, very good. This is the stoichiometric restriction. This is the, as already I have written, stoichiometric restriction on the composition. Only one. Equalities. Equalities mean restriction on the composition of each phase. One restriction. First of all, okay. Okay, you see why it is applicable. I will show you. Take up one by one. Calcium CaCO3. Does it hold good? Let us see how many O here. 3O. NO is 3. In case of calcium carbonate, I am showing you. Calcium carbonate. You apply. NO is how many? 3. NCA how many? 1. 1 plus 2. NC how many? 1. 2 into 1. So makes sense. That means this holds good. Look at 3 is 1 plus 2. Calcium oxide. Apply. NO is how many? NO is how many? 1. NCA how many? 1. Plus 2NC. 2 NC is how many? No carbon. So holds good. Last is carbon dioxide. What is NO? 2 is what? NCA. NCA is how many? No CA. Plus 2NC. NC is 1. Whole goods. So these are satisfied. So that means this relation holds good for each of these phases. Now it is actually another step you may jump. Another step you may jump. That this means these elements has the number of components. As you number of components means number of species. Then what happens? I tell you, species. Then you actually have no. If the species mole fractions are bound, remember concept of species. The previous discussion. If the mole fractions are bound, chemical potential same. The mole fraction finally mole P minus 1 restriction on the composition mole fraction. This I showed from the equality of chemical potential partial molar free energy activity mole fractions like this. So mole fractions of species, and here if you just pretend that elements are actually components species. This serves as species. CaCO3, but their compositions have a have dependence, mutual dependence or relations, or what is this called? They are related. They are related. Okay, the compositions are related. Then you have actually this compositional restriction is coming there. Okay, like this previous case species. So if you pretend this, then you what will do? You divide by n total or divide by n total, divide by n total, divide by n total, and what it gives rise to, or XO, mole fraction. Ni by n total is the mole fraction or atom fraction. Mole fraction of O is XCA plus 2XC. Yes, this is a compositional restriction equation. How many? One equation. How many? I'm sorry. How many equation? See, number is how many? Number is 1, because this relation is why I wrote first, the relation is 1. Okay, this is 1. Composition of these 3. So number of elements here, since for this restriction you have actually 1 less than the number of elements. So 3 1 less 3. Okay, so that is 3 minus 1. 3 1 taken away from 3 is 3 minus 1 is 2. So 2 is 2 and 2. Okay, so now they are reconciling. Now they are reconciling. Okay, now this is actually, so it is about the third example. Still another example I will take. Another example I will take here. What I am taking take is I write here. Yeah, good, very good. Just don't have to here. Good enough. 3. Third example. See, check. I am giving you the system as MgO. MgO solid. A system. Non-reactive. No, just MgO. What is the number of components? C is what? So you apply your concept, number of species minus number of reactions. I am not writing this independently. Number of reactions. How many? No reaction. This is a non-reactive system. MgO alone. Where is the reaction? So 0. So number of species. How many species? MgO alone is 1. COE number of species 1. Species is MgO. What is the species here? MgO single. MgO. Okay. 1. So C is 1 by according to this definition. According to these elements now elements against C, from the viewpoint of elements, number of elements is what? What are the elements? Mg, as I have told you, Mg, O, element MgO. So C is 2 minus restrict. First of all, 2 is clashing with 1. 2 different from 1. Then where is the wrong? This 2 is not correct because there is a stoichiometric restriction. MgO is a stoichiometric compound. So stoichiometric. What is the restriction? 2, let me write. This restriction, 1 restriction is there like here. So 2 minus, shall I write first of all, number of elements. C is number of elements I am removing this line, no problem, no problem. Number of elements minus, write this, number of stoichiometric restriction. Number of stoichio restrictions. What is this? Remove this line. So what is number of elements is what? How many? Clearly 2. Clearly 2. If you don't consider this, ignore this, then it will be 2 and 2 and 1 are different. But you know, this has this is actually significant, and this is to be considered. Okay, number of person restrictions. This actually restrictions holds good here. There are restrictions, and this is actually valid number. Okay, or say this is actually non-zero. So what is this? 2 minus, let me write number of restrictions 1. I am showing you 1 is what? 1. Then it is reconciled, these two. But what is the restriction that I have to? Can you tell me what is the restriction here? In the way you wrote there, NO is NCA plus 2 NC in case of calcium carbonate reaction. Second example. So here, what is this? What is the restriction? NMG is NO. NMG is NO. See, how many moles of magnesium? 1. Moles of atom. Atom of oxygen, magnesium 1, oxygen 1. NMG is NO. Number of, you may call it gram mole or gram atom of magnesium and gram atom of oxygen. You write O means gram mole or gram atom is same. And here also gram mole or gram atom same. So 1. Or 1 atom, whatever you use. But use the same scale in each case. Atom, gram mole, like this. Okay. But anyway, that is different issue. NMG is NO. So this is the restriction. How many? 1. One equation is one restriction. But it is better as I have said, use in terms of mole fraction. So as if you treat this Mg and O are actually two separate species actually. So what you do? Or NMG by N total is NO by N total. N total means NMG plus NO. Here N total. So or what you get? XMG is XO. Mole fraction of Mg is mole fraction of O. What is that value? What is the mole fraction in MgO? What is the mole fraction of O in MgO? How many? 1 out of 2. So 0.5. And Mg likewise 1 out of 1 plus 1, 2. 1 out of 2. 1 of Mg, 1 of O. So 2. So both are same is 0.5. So mole fraction is fixed actually. So this is this. So this gives you, you can write both. This gives you the equality. So mole fraction composition restriction. So yeah, you cannot choose. In MgO, you have no choice. On composition, you cannot say mole fraction 0.6 of magnesium. I want to choose 0.6 mole fraction magnesium. No, that is not MgO anymore. 0.3 of oxygen I want to choose. No. But if it were, however, if it were Mg and oxygen solid solution, okay, so but okay, this is answer to this one. This is stoichiometric restriction. Stoichiometric restriction on composition, on the composition, single phase restriction on composition, because mole fraction is composition. Okay, see, as I told you, you treat Mg as a species here, concept of species, two species MgO, but they are bound. Then actually you have actually compositional equal that acts as a dependent variables or restrictions or equalities, equations, equalities are there. One equalities is there. Okay, so then your what happens? Equalities then you see number of species minus number of independent reaction equilibrium. So that is restriction. So this is decreased. Species decreased. So here also species. This came from reaction equilibrium. This restriction came from number of independent reaction equilibrium came from reactions. Chemical reactions gives rise to restriction because of equilibrium. Activity same at equilibrium or say delta G is 0, chemical reactions. So finally it gives rise to activity and composition along with temperature, pressure is a so restrictions. Here also restriction on the composition. So MgO treated as two species, but they have a restriction. So they become the two cannot be. So taking these restrictions are taken away from number of species. So two species MgO minus restriction, number of restrictions 1. 2 minus 1 is 1. C is okay. C is that way you can also consider, or you consider this restriction on composition. On composition, the restriction it cannot be. You cannot violate this. That means there is a restriction. When you can violate, you are free. You are free to violate. That actually gives gives an impression of freedom. You can violate freely, free to. You are not bound. You are not actually under compulsion. That is should be 0.5 always. But however, when you are free, example, if it were not magnesium oxide compound, but however in MgO solid solution, MgO solid solution or liquid solution, that can dissolve, oxygen is dissolved, liquid solution, then XMG here you can choose XMG any value 0.8. This concentration is small though, but there is a choice. XO is very small, say XO you choose say 0.1, 0.2, 0.01, anything you choose, and XMG will be balanced. So you can choose. There is a range over which MgO solid solution exists. It's a domain over which it is stable. A domain of composition. Domain means range. 0.1, 0.01, 0.2, and then XMG. Then actually XMG will be automatically the balance difference. 1 minus 0.1, XMG will be 0.9. No doubt. So not 0.5. Here rigid, inflexible. This is flexible. Thank you. I think we have been able. Okay. So we have been able to express this. I do not know whether. Hello. You can check this. Just check. If it is, you can see this 0.9. Just it is visible. To? Thank you so much. Okay. Thank you. Above this one, this visible. To? This one. This mark is visible. To? Yes. No? Okay. That one, 0.9. Yes, it is visible. XMG is 0.9. My pen is here. Visible. Visible. To? I will not go beyond this. No? This is the limit. No? The lowest limit. There is still space. This space I think today there is space. Thank you. So with this actually the concept of component is over. So now we will take up. So let me remove this Remove this, remove all. Only the title, the Gibbs phase group. And let me write F is, let me write somewhere, F is C minus P plus 2. This is your Gibbs phase rule. This is the Gibbs phase rule. This we will discuss further. What we will discuss? We will application of this Gibbs phase rule to illustrate this phase rule. Okay. So this will be the next job. So next job is what? Next job. Oh, by the way, another point. Acha, you give this. You give a star mark here. Hmm. Another point. Let me finish. Then I will take up. Okay. What is this? This is also another thing pending. This is important. So components have two alternative definitions. So degree of freedom also kind of alternative. I'm giving you alternative definition of the degrees of freedom. What I have already given, the number of variables. It gives the number of variables that can be independently varied to or which are required to describe the state of the system at equilibrium. The number of variables that are required to define the state of the system at equilibrium. So, this is actually the degree of freedom. Number of independent variables. Okay, very good. So alternative. This let me finish this. Alternative definition of the degrees of freedom. F. This is also let us write this out. The degrees of freedom of a system under chemical equilibrium is the number of variables that can be independently varied, or you can call it specified or fixed or specified, whatever term you would like to use. Specified, all same thing. Specified, also specified without changing number of phases present in the system at equilibrium. This is the alternative definition. I give you the subtle difference, or same thing I am saying. First, what I said, the original definition of the degrees of freedom is that I said, what I said, the number of independent variables that are required to define the state of the system at equilibrium. Number of variables that are required to define the, because phase rule applies at equilibrium. I repeat, the number of variables are independent variables. That's mutually independent, like temperature, pressure, mutually independent. So moles. So number of independent variables that are required to define the state of the system at equilibrium, this we know as degrees of freedom F. Here also I am saying that what I am saying, you can, these are the numbers. This number is such that you can vary this number without changing the number of phases of the system. This see. It can be independently varied. It can change. Suppose degree of freedom is 2. These two variables can be changed. Say temperature. Two variables you consider temperature and pressure. So temperature can be changed over a domain, though over range, but change. Size change means change. Little change means change. It can be changed. That pressure also can be changed. If you have 2 degrees of freedom. And when you change, there is no change in the number of phases. No phase will be eliminated. This is. So without altering, without changing the number of phases, phase will remain same as before. So if phase was 3 phases, the 3 phases will be there. But and your degrees of freedom 2, you change freely. And first definition was what? To define the state of the system, you have to specify these independent variables given by the number of freedom, degrees, given by the degrees of freedom. So suppose degree of freedom is 2, then you have to specify these 2 variables. Specify these 2 independent variables to define the state of the system. Specify again number of variables to determine. Yes. So what I said that these suppose the degree of freedom is 2, so 2 variables are required to define the state of the system at equilibrium. This 2 is important. Which 2 is secondary? It may be temperature, pressure, it may be temperature, composition, etc. etc. Pressure composition. So here it is said the same thing in a sense that these 2 you can freely use. When you are specifying, you are freely altering. When you specify, say T is 800, means you can change this to 900. When you specify, freely specify, means you can alter it. When I say fixed it means arbitrarily fixing it, means independence. Fixing means not dependence. You are fixing your own choice. You are independently fixing, arbitrarily fixing, or specifying, varying. 800, I am varying, I don't like this 800. 850 degrees Kelvin, etc. Pressure is 1 atmosphere, no 1.5 atmosphere. So these are the hallmarks of a degrees of freedom. Here also it is says that if you change this freely, number of phases will not change because this is your freedom. So why number of phases will change? Means no phase will be eliminated. Now you see, if you don't do this, now you see, if you exceed, now 2 questions comes. Suppose degree of freedom is 2. If we exceed this 2, you venture into specifying more than 2. You are entitled to specify or choose, arbitrarily choose 2 only. But if you want to, intend to change 3, more than 2, violate the degrees of freedom, exceed, then what will happen? Similarly, if you don't apply the requisite number of variables, or you actually say you fall short of fixing the number of variables compared to the degrees of freedom. So that means if you actually fix fewer number of variables than the degrees of freedom allows. So 2 is the degree of freedom. You don't fix 2, let alone 3, not even 2. You are fixing, you are under fixing, under specifying 1. Then what will happen? So 2 cases. One is more than degrees of freedom, another is less than degrees of freedom. You are specifying more than degrees of freedom F. Exceeding, another case you are falling short of. Then what will happen? This should be additional comments. So comments. Okay, this is definition already over. So in this light, if the degrees of freedom is exceeded, what will happen? Violation. You are violating degrees of freedom, but exceeded in terms of exceeding more than degrees of freedom entitles you. If the degrees of freedom are exceeded, a new equilibrium will be established. Note this: a new equilibrium. It is not that a new equilibrium will be established. In the system with fewer phases. This you have to understand. Yes, if you over exercise the degrees of freedom, exceed the degrees of freedom, suppose it is exceed the degrees of freedom, suppose it is 2, you are fixing 3 arbitrarily. Then what will happen? Then one phase, more than one, okay, number of phases, or some say number of phases, or a few phases, or should I say, or say one, or okay, or phases, or some number of phases will have to be sacrificed, eliminated, which will result in the elimination of number of phases, certain number of phases. So suppose you exceed by 1, 2, 3, then one phase will be eliminated. Means you will not have in the system same number of phases, it will be 1 less. If we exceed the degrees of freedom by 1. So it is clear here, clear. F is C minus P plus 2. What you have done? You have exceeded the degrees of freedom by certain number, say 2, say 1, say 1, then it will be obviously minus. So down by 1. number of phases. Exceed, sacrifice phase. This is the consequence. So this is about the increasing. Okay, this is so fewer phases. So P will down. So this is okay. So if you exceed by 2, if you ask exceed by 2, then 2 phases will be eliminated. Down this. Okay, this is this. Okay, very good. C minus P. On the other hand, so this is about if you have exceeded, if you fall short of, then on the other hand, if the number of applied freedoms falls short of the degrees of freedom, the what happened? The state of the system will remain undefined. This is very important, equally important. So suppose your degrees of freedom is 2, so you have to fix 2 variables. It is understood that they are mutually independent, like say temperature, pressure. Okay, so say 2 here, 2, but you are not specifying 2. You say no, I will under specify 1, temperature only. Then what is the pressure? What is the, then the system will be defined. Then system will remain undefined because you will ask what is the pressure. You will ask also composition, all these things. Okay, so all when all are known, all are specified, then the system is defined. State of the system dependent, state of the system is defined. That is the job. State is fully defined. This is the state of the system. Another thing I tell you, I forgot to tell you last day. Yes, I told you, but some properties I didn't consider. When I say the properties, millions of properties. So temperature, pressure, I said. So do you have to say you only actually have a limited number of independent variables are required to define the state of the system. So 1, 2, 3, 4, sometimes none, we call invariant system. 0 degrees of freedom. 1, 2, 3, 4, 5, 6. But properties are actually hundreds, thousands, millions, like say temperature, pressure, volume, composition, moles, mole fractions, mole, heat capacity, viscosity, surface tension, all properties. Okay, and then also you take other other properties, thermodynamic properties, internal energy, enthalpy, entropy, and so on. Okay, there. So these properties of thermal conductivity. So they are all actually seen when temperature pressures are specified. those properties are also specified. They are dependent on temperature, pressure, and moles. Moles. For example, temperature, pressure, moles, volume, ideal gas, for example. Easiest, the equation PV is nRT. So volume cannot be independent. But if you treat volume as independent, then maybe pressure will be dependent, will not be independent. V, T, and N is known like this. So that is understandable. So you see, now if you have not specified the requisite number of variables, which is called the degrees of freedom. Suppose which is 2. Supposing it is 2, it helps if we consider some value 2, and you don't specify this 2. Only one, the pressure. Then obvious the question comes, what are the other values? What is the other variables, like say pressure, what is the temperature? Mole fraction, see, if it is a single species, mole fraction composition will be 1. That's understood. But what is the temperature? So you have to specify. So unless you do this, it is not defined. System is not. This is the consequence if you under specify, and that is the first part is if you over specify, exceed the degrees of freedom, then elimination of the phases. Then elimination of the phases. F increases, P decreases. That's it. That's it. Now is the time to take up some application of the degrees of freedom. So application of the Gibbs phase rule. Okay. So just let me clear this part. Okay. This will be helpful. If I clarify this, is okay. So remove this. Remove this. All okay. Remember this. Okay. This is the two relations. I don't write anymore because I have already written number of times. So you will remember this. So I tell you what. I will consider a number of examples, 12 examples, one by one, to illustrate, and what we'll do to application of the Gibbs phase rule, and 12 examples will take up, and what we'll do, we'll find out the degrees of freedom, and then we'll show how by fixing this F number of degrees of freedom is F number of variables, the state of the system is specified, defined. State of the system is defined. By fixing this number of variables, fixing means specifying, varying, specifying, fixing, all the same thing. So this will show. So I am removing this. So next job is actually the application of the Gibbs phase rule for the purpose of illustration. How many minutes left?
1 hour 35 minutes, 125 minutes.
It's okay. You come in time. Hello, Bapu. Just see if this line you can see.
Yes, yes.
Okay. So now applications of the Gibbs phase rule. Of the Gibbs phase rule. This is the Gibbs phase rule. You see on the right hand corner, F is C minus P plus 2. C is the number of components and P is the number of phases, and F is the degrees of freedom. Okay. So this, what is this objective as to find how will demonstrate the applications, how will you progress with the application, to find, first of all, find out the F using this okay, what is this called, this small relation, F is C minus concise relation C minus P plus 2, find the value, then demonstrate how by using this F number of variables state of the system is defined at equilibrium. Okay, this is to find the, this is the application. So first of all, to find the degrees of freedom at from the phase rule and to demonstrate how by fixing, one thing I tell you, when often I will use the word fixing, fix this variable. We fix the temperature as 500 Kelvin. We fix the temperature as 1000 Kelvin. That means it is arbitrarily fixing. Because we are fixing, means it is a sign of independence and freedom. Independence, freedom, arbitrarily fixing. It is not fixed means it is not dependent or say it is not it is not a sign of independence. No, fixing is arbitrarily, independently fixing. So it is an independence. When it is, if it is fixed for us, it is automatically fixed for us, then that is not called fixing. Because we don't have to fix, it is fixed, already fixed. Like triple point, no freedom, all fixed, no, no variation, no flexibility, not a not a jot of flexibility, not a speck of flexibility, not not no flexibility altogether. Rigid. That point means that points are already fixed for you. Triple point of a single component. Zero freedom. Solid water, water vapor, and ice. Example. Just for example. They are fixed. They are already fixed for you. But when I say I fix, fixing means I am fixing, means arbitrary. So by fixing, and that is actually related to the degrees of freedom, okay, or independence by okay, by fixing f number. How? By fixing f number of variables. The state of the system can be completely defined at equilibrium. 12 means 12 examples will be considered, will be taken up for the purpose of illustration. So, we see another, so first thing is two things you remember. First is find f, the degrees of freedom, using the phase rule. Okay. Then what you will achieve? Suppose I get it f is 3. So what L I'll do? What on earth I'll do with this f is 3? Now, by fixing three variables now, f is 3, you can define the state of the system at equilibrium. Define the state is fully defined just by 3, yes. Because all other host of properties on earth will be dependent on this 3, will be dependently fixed, as I said. You have defined temperature, pressure, heat capacities will be fixed. Thermal conductivity will be fixed. Internal energy will be fixed. So on, okay? And as another thing, always remember in the phase rule, in the derivation is very important. The moles of each phase, for given number of moles of each phase. If there are three species N1, N2, N3, 1, 2, 3, N1, N2, N3, 3 are not 3 moles. All 3 cannot be independent because the derivation intrinsically consider for a given size of each phase. Means total moles of each phase a given value. So all we cannot be independent. Two of them. Suppose there are 3, 2 independent. Third will be dependent on the total and the other 2. Suppose total number is say 5. We have considered say first one N1 is 1 mole, N2 is 2 moles. Then how many? What is the N3? N3 you cannot choose anymore because 6 is the given size. So C will be N3 will be 6 minus 1 minus 2 is 3 automatically. So remember this part is very important in the derivation for given size of each phase. And later on we consider this modified given size is 1 mole. Then 1 mole, then moles becomes mole fraction. Contribution of becomes mole fraction. And mole fraction always also you know, and all mole fraction cannot be fixed, cannot be variable because total sum they sum to the total as 1. total to a value of 1. So all mole fraction add up to 1. Or the sum of mole fraction is 1. So careful about this. This is, and considering this, with this we have arrived at. Once we have arrived at this, this already means that yes. But in the back of your head, you okay, inside your head keep this. The derivation has tacit consideration that given size of each phase, it is not all phases together. For each phase, size is fixed. So these are the important points. Fine. So after derivations considers okay equilibrium considerations constants, and we have arrived here, and then you find f for 12 examples. In each case, find f, and then show how by fixing this f number of variables, state of the system can be fully defined at equilibrium. So this is okay. 12 examples. First, start. First example, I will write this one, two, write this way. The simplest M solid plus half O2 gas goes to MO solid. This is a reaction equilibrium reaction system. So I can show you how it is in a sketch at equilibrium. We will apply the phase rule at equilibrium. Degrees of freedom pertain to equilibrium. At equilibrium, because you actually got these dependent variables that you subtracted from the total, they came from the equilibrium consideration. At equilibrium, pressure is alpha, pressure of alpha is pressure of beta phase, is pressure gamma phase pressure at equilibrium. This is called pressure equilibrium, mechanical equilibrium, thermal equilibrium. So equilibrium is very much there. So that's why you got so many restrictions. So at equilibrium, so phase rule applies at equilibrium. Okay, and that chemical equilibrium, as we said, which includes pressure temperature constancy, dg pt is 0. So these are all considered. Okay, so so considering all this, you have these choices, and you will learn more as you discuss the examples. Okay, so suppose this is your pressure, p is the total. This p, when I write, p is the total pressure, and partial pressure is pi, P subscript I, okay, P total pressure. This is the temperature, as we know, temperature. See, whether this is, they have actually, they are actually independently, they can be varied or fixed, that will be subject to the values of degrees of freedom. Don't worry, system I am showing you: metal solid, metal solid, metal oxide solid, and this is oxygen gas. Picture, equilibrium condition. What we will do? Find the degrees of freedom. First thing. So do this. Do this. F is C minus P plus 2. Write this. C is what? Write this here. C, find out here alongside. C is how many? Two definitions are there. Number of species minus number of independent. I am not writing independent reaction equilibrium. Okay. This automatically independent reaction equilibrium. So one equilibrium says how many species? How many? 1, 2, 3. Minus 1 is 2. Is 2. So C is 2. Species. Which are species? Which are species here? Write this. Species. How many? 3. Which is this? M solid, MO solid, oxygen gas. Number of reactions clearly seen. Oh, Or alternative definition is what? Number of elements you want to be satisfied. Cross check always. Number of elements, check this. Number of elements. There is no question of any stoichiometric restriction. I tell you what, this is very good actual tips that you consider stoichiometric restriction when you will see the phases involved are bound type. All, 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 all. No, it is not actually one of them. So this is bound, but that doesn't suffice. All of them, all phases. Example is calcium carbonate goes to calcium oxide plus carbon dioxide. So bound. Calcium oxide is a bound. CaO, CO2 bound carbon dioxide. Calcium carbonate CaCO3. Then you know stoichiometric restriction will apply. Also another example I gave you, magnesium oxide, MgO, alone, single, bound. So number of stoichiometric restriction you write. Otherwise number of C is number of elements. Okay. So it is what how many is some minus stoichiometric restriction. I am not writing actually number of 0. So I am writing for the first case number of stoichio restriction on compositions, etc. etc. This is simply 0. Meaningless. You are free, I am free. 0. So elements is how many? Periodic table elements M and O is 2. Like say element. You may write MO. Very good. MO, okay, 2. So both cases 2 means you are satisfied. So move on. AP is C minus P plus 2. So C is 2. How many phases? P is what? Right? P is how many phases? Let us see. Phases. See. Solid. So these are pure solid. They are not miscible. So normally, any two things cannot be 100% immiscible. All things are miscible in all other things. Okay. Any substance are miscible in any other substance. Okay. To varying extent. Maybe very small, but in principle it should be because this is a free energy of mixing is negative. So it will mixing is a spontaneous process. So we will not take up these fine things. We consider it is pure means pure. So pure. Two separate phases and gas phase. So 1, 2, 3 phases. We write here. Let's say right here. Phase is 3. 2 solids. What they write in bracket MO solid and one gas. 3 plus 2 1 degrees of freedom. By fixing one variable, your system is fully defined because others will be automatically fixed. Pressure, suppose I fix temperature, pressure automatically. Yes, under the compulsion of this equilibrium. So what is it? Let us try. I fix, for example, temperature. One temperature. Temperature can be chosen as anything else. Okay, let us fix temperature. 1. I'm writing 1 temperature. Say temperature. Say as temperature. Say 800 Kelvin. I am showing you. Just to show you practical example. 800. I have chosen. See, I can choose 900. 1 degrees of freedom. Right? Temperature. Only one. Say. It is better you write say. For example, I have arbitrarily. Then what will happen? Let us move on to this. Then you see fixing temperature. What is this? Oh, AP you have found. Then actually I tell you what. I tell you what. AP is 1. First part is over. Find the degrees of freedom. Then show. Then demonstrate. Demonstration of the phase group. then you have to show by fixing one variable, all other, like said, namely, we actually okay, emphasize on temperature, pressure, composition. Okay, because these three things. Okay, and all other will be automatically fixed. Okay, so then demonstration. We will demonstrate by fixing a number of variables. The state of the system is fully defined in terms of temperature, pressure, and composition. As you know, state of the defined means temperature, pressure, composition, all. Then we'll be satisfied that this is defined. Demonstration. What is the demonstration? T. Right? Fixing T. See. Fixing T fixes what? You know, equilibrium constant as a function of temperature. Fixing T, I have T fixed as 800. Just plus T I am writing. KT. Fixing KT. KT is what? Tell me, is what? Okay, you write here in case you are interested. Is KT is what? K800. Just to help you. For example, is what anyway? KT is what? Activity of MO. Activity of M. Activity of gas is partial pressure, you know. So partial pressure of oxygen powered up, and you may write these are all pertain. These all pertain to equilibrium. Happy. And also you write here activity MO since is a pure substance means standard state, and this is also standard state. Activity is 1. So what you get here? Shall I write here? Is 1 by PO2 power half equilibrium. Equilibrium. So KT is fixed. I am giving a tick mark. Fixed means known. T I have chosen 800. So KT is known. K is a function of temperature. From delta G0 is A plus BT. Is minus RT ln K. You know, 100 times, million times you have done. So if this is known, then this is known. This leads to what is known? PO2 equilibrium is known, or P is also, or P is total pressure is PO2 is known. What is the total pressure? The only one gas species, so because only one gas species, that is oxygen in the system. So its pressure is the total pressure. Partial pressure of oxygen is the total pressure. So I know temperature I have fixed arbitrarily from my allowed degrees of freedom, from the permitted degrees of freedom, only one, and then pressure is known. So what you composition of each phase mentioned. So composition is defined the composition. Okay, you take. So so composition of each phase is known. What is known how? M solid. How many minutes?
1 hour 59 minutes 24 seconds.
अच्छा ठीक है, 2-3 minutes. It's almost done. 2 minutes. M is pure, metal solid pure, as you know. So what is this? A mole fraction alone, a separate phase itself constitutes a separate phase. So xm mole fraction of m is in that phase is 1 alone. Composition, mole fraction is composition. MO solid pure. So what is the XMO? If they are in solution, then they would share the mole fraction. So together would be 1. but they are not in solution, so pure. And oxygen gas phase, gas phase is what? About gas phase, what is known? PO2 is known, okay? Or this gives you what? See, PO2 is what? XO2 mole fraction of oxygen is what? PO2 by total pressure. These are same. PO2 is P. This is P is 1. So all compositions fully defined. Temperature pressure composition of each phase. This is the utility of degrees of freedom phase rule. This is actually the application or beauty of the Gibbs phase rule. This is the service of the Gibbs phase rule. So we, by fixing, found this part is over. Then actually I tell you what, okay, then I will construct a stability diagram, okay. This is in addition, I am writing it. Next class I will stop here today. Stability diagram, I tell you what, I will construct the stability diagram here, a rough sketch. Why I am drawing, we will consider drawing stability diagram after these examples are over. 12 examples are over, then we will separate topic, construction of stability diagram. We will learn about this. That we will do. And we will take more complicated systems there, elaborate systems. Here is a simple system. This we will do. Okay, this will draw stability diagram. Okay. Okay, this actually, this I am just showing you. This is actually ln PO2. Hello, done. Versus 1 by 2, 1 by T. This is actually, this I will show you. MO both together. Here is MO solid. Below is M solid. This type of thing I will actually explain you next class. Not today. Today, this time we will be going to how I do this. I will give you, but elaborate, okay, elaborate learning of stability diagram will be taken up later. But in each case, 12 cases may not be all 12 cases, but in some cases or quite a few cases, we will draw the stability diagram because there is some relation between the phase rule and the stability diagram. With the help of stability diagram, we actually kind of show how the phase rule works here. Okay, one application of this actually, the phase rule, application of phase rule can be understood from this diagram also. They are kind of intertwined. They are related. They are related. They are not actually. See here also. What is the degree of freedom here, etc. Like this. What is along this line? What is this? What does it mean? How we got the line? So this is actually they are really interrelated. Degree of freedom and stability. That's why we will construct the stability diagram. But formally, we will take up the stability diagram after these 12 examples are discussed. Thank you very much for your patience and for your cooperation and your interest and okay, your sincerity, etc., etc. Thank you very much. See you next class. Bye.